So this first lesson should be pretty quick, pretty short. It's fairly simple. Okay, gives you the general idea of what we're going to do. We are going to move away from derivatives. Okay, we are going to start integration with this chapter. Okay, now one of the key reasons why integration exists is I want the area under this curve. Okay, so let's talk about how we find that. Now, specifically, when we say area under the curve, you need to know the area under the curve is always the distance between the curve and the x-axis. Okay? The only time that changes is if they're talking about the y-axis. Okay? Because sometimes they will put the y-axis, which means you need the function in terms of y. Okay? So if the function's in terms of y, then they're talking about the distance between the function and the y-axis. If it's in terms of x, generally that's the way it's going to be. I'm not going to start anything too crazy. We'll do more interesting stuff later on. But right now, it's just this area right here that I want to find. Okay? So for that first graph. For the second graph, it is this area. Okay? And for the third graph, this is where it gets a little tricky. It is, again, the area between the function and the x-axis. So that is the area we're looking for. Now, so the function itself is the rate of change function. The area under the curve gives us the accumulation of that change. Now, for example, you're on a road trip and your car is on cruise control for 4 hours. Okay, which means you have nobody else on the road with you because you travel 60 miles an hour. How far have you traveled after those 4 hours? So we are finding the area right here. Half hours. Now, the nice thing is because you were at a constant rate of change, 60 miles per hour for 4 hours, that should be pretty obvious. How far have you driven if you drove for 60 miles per hour for 4 hours? Yeah, 240 miles. Now, our answer is going to be in terms of just the accumulation of change. So if you take the fact that we have 60 miles per hour times 40 hours, 4 hours, the hours are going to cancel, giving you that 240 miles. You may wonder why I'm moving so quickly through this. It's because the next unit is a little long. I'm going to get through that as well. So, the dependent unit is multiplied by the independent unit. In other words, the unit for y times the unit for x. In most cases, we're going to drop the unit for time. That's what's going to cancel out. Now, what gets a little more interesting is not every shape is going to be that nice linear function. So the graph represents the rate at which water is leaking out of a tank. Their units are given on the graph. How much water is leaked out after 9 minutes. Now, what we can do, because we all know geometry, is we can break this into shapes that we can recognize and find easy areas of. So for example, I can create this rectangle and say that area is length times width, which is 6 times 2, 12, and it is gallons per minute, so gallons. This area, that's triangle, area is 1/2 base times height. So that is 1/2 of 4 times 2, which is 4 gallons. This area is a semicircle. Area of a semicircle is 1/2 pi r squared, and the radius is 2. So 1/2 pi times 2 squared, which is 2 pi. So add that up, gallons. If you want to leave it in terms of pi, you can say 16 plus 2 pi gallons. Okay, or we can I have my calculator here, so 16 plus 2 second pi. 22.28. 3 gallons. One thing I will say is do make sure you go to 3 decimal places. That's kind of the standard for the course, is to go to 3 decimal places. So when you round, do not round to 1 decimal place, go to 3. I had to write that out in a couple people's tests, especially when dealing with pi. So in some instances, it's not too bad. Again, we can easily find the area of these shapes. All right. Particles moving along the x-axis modeled by this function in centimeters per second. So our answer is just going to be in terms of centimeters. How far is the particle from the starting point position after 10 seconds? So that's all the way down here. Now, anything above the x-axis, what's going to happen? So if it's above the x-axis, yeah. So, well, in terms of particle movement, okay, anything above is what? To the right, anything below is to the left. Okay. So now, when we state this, just like you think on the test, it talked about moving particle position up or down. This one is left or right. So we are going to find the area, anything above, we are going to assume is a positive area. Anything below is going to be a negative area. So we have 2 triangles up top. So it moved to the right. How much? Well, that is 1/2 of 2 times 10 plus 1/2 of, well, also 2 times 10. So it moved 20 centimeters right. Total. Right. To the left, now again, if you want, you can break that into 3 different shapes, but I'm just going to use the fact that this is a trapezoid and the rule for a trapezoid. So left is 1/2 the height, which is negative 15, times the sum of the bases, which is 2 and 6. So where this right here is 6 and this right here is 2, height is 15. Now again, you don't have to do negative 15 because we know we're moving to the left. We can just say it's a 15. So 1/2 of 15 times 2 times plus 6 is 1/2 15 times 8, which is 15 times 4, which is 60 centimeters left. So total change would be what? 40 centimeters to the left. Now, how far is the particle from a position at t equals 2 seconds after t equals 8 seconds? So here they just want to know what's the change from 2 to 8. Okay, which we already found. We already found that to be what? Left 60 centimeters. So there it is. I don't know. Where's that? just two ways to ask a question. One way is what is the total from 0 to a certain point, and then what's the change in position between two specific points. So again, you know your basic area formulas, not bad. Okay, that's all this first lesson is the concept that we are trying to find the area between a function and the x-axis. So not too terribly bad. Let's go to the next lesson. And let's talk about Riemann sums. Now, the graph of the function u of x is shown on the right. Approximate the area of the curve on the intervals from 2 to 6. So just from here to here. Okay. Now, we are going to use what's called rectangular approximation, specifically left rectangular approximation, which means the height of our rectangle is based on whatever the height of the left side is. Okay. Now, if I just use one rectangle, okay, my width of my rectangle would be the change in x. Okay, again, if I just made this one rectangle, my width would just be 6 minus 2, which is 4. Right, that area would be whatever, 4 times 2, 8. I don't have any units, so I'm just going to leave it as that. Now, if I change this to have 4 rectangles, so I have this rectangle, this rectangle. Again, I'm using the height of the function on the left side. That's what the left approximation is. So I have these 4 rectangles. So again, the width would be 6 minus 2 over 4. So you take how many intervals and divide your total width by the number of intervals. So I would have a width of 1. Now, I would actually have to, and I can't actually do this here because there's no way to know the function. All right. I could do it at the beginning because I knew the height at 2. I don't know the height at 3, 4, and 5. So I can't actually find this without actually knowing the function itself. And this function is not simple enough to guess. So that's just showing you how I would find the area. Now, let's say I wanted 8 intervals. The width would be 6 minus 2 over 8. So my width of each rectangle would be 1/2. So here we have each rectangle. Now, you should be coming across an idea here. All right, should be coming across some little idea. As we increase the number of rectangles, what happens? We get a better and better estimation. So, does anybody think they have an idea of where this is leading to? Just curious. You don't have to answer. Just curious. Do you have any idea where this is leading to? If I'm increasing the number of rectangles, how can I get the best approximation? Infinite number of rectangles. So we would take the limit as the number of rectangles goes to infinity. Right? Now, the nice thing is we're not going to do that today. Okay, we're just going to stick with approximation. Now, this is called the Riemann sum approximation. So, named after the German mathematician Bernard Riemann. Um, so, yeah. Now, here we actually do have a graph, and we do have a function for the graph, so we can actually find the x and y values. So, below is the graph of the function f is equal to 4x minus 1 half x squared. Use Riemann sums to find approximation of area under the curve. Now, there are 4 different Riemann sum approximations we can do. We're going to talk about each 4. One is the left, which we just saw. Again, we're taking 3 subintervals starting from 2 all the way over to just 8. So that means I would take this distance, which is 6, 8 minus 2, over 3. So it gives me 6 over 3. Each rectangle would be a width of 2. Now, we are using the left value. So we are basing the height of the rectangle on the value of the left side of this rectangle. So now the nice thing is we can easily see what the height of each of these is. So that's real nice. All right. Here we have 2 times what? This is 6. This is 2 times 8, and then 2 times 6 again. So it gives me 12 plus 16 plus 12, which is 40. Same shape, same number of intervals. But this time we are basing this on the right Riemann sum. So we're basing the height on the value to the right, which means that's not good. Try that again. So this would just be 0, because the height of that is 0. This would be 2 times 6 and then 2 times 8. So that would give you 16 plus 12, which is 28. So left Riemann sum, we use the value to the left. Right Riemann sum, we use the value to the right. It'll tell you which one to use. Yeah. Yeah. It'll say use the right Riemann sum, use the left Riemann sum. It won't have you pick your favorite. All right. Now, this one would seem a bit more obvious. This would be the one that I would probably go to, the midpoint one. Okay. So here we're going to again make our triangles. I'm sorry, rectangles, not triangles. Okay. But we are going to base the height of the rectangle off the value at each midpoint. So I'm going to find f of 3, f of 5, and f of 7. Using the fact that what was the equation again? 4x. So f of x equals 4x minus 1 half x squared. So being that I don't want to do that, I'm going to go put it in here. So 4x minus 0.5x squared. Go to my table set and change that to ask, and then table. So delete. We have 3, 5, and 7. Okay. So this right here. Oh, that right there. And that right there. So it's going to give me 2 times 7.5 plus 2 times 7.5 plus 2 times 3.5, which gives me 15 plus 15 plus 7, which is 37. Now, is there an easier way to do that? let's go back here real quick. We got the left side was 40, the right side was 28. We got the midpoint was 37. How can we use the left and right side to get the midpoint? Average them. Yeah, if we took 40 plus 28 over 2, that gives you 68 over 2, which is 37. So, if you are asked to find the left, right, and midpoint, don't waste your time on the midpoint because you already found your left and right. Just average your left and right. Hmm? It's not 34. Did I add that wrong? So, no, that should not be 37. Should be 37. What did I do wrong? Oh, no, no, no. I'm thinking the wrong thing. You're right. It is 37. Let's look at what's going to happen next here. Yeah. I'm thinking of the wrong one. The midpoint, yeah, you still have to find midpoint. Trapezoid. Now, trapezoid, you would think, honestly, would be your best approximation. Because what we're going to do when we make our shapes here is we are going to connect our left and right side like so. So with that, what we have is the least amount of wasted space or added space. Now, we kind of just talked about area of a trapezoid. Area of a trapezoid is 1/2 the height times base 1 plus base 2. In this case, it is 1/2 the width times f of, well, say x1 plus f of x2. So since my width is 2, it's 1/2 of 2 times, we already know that at 2 I get 6, at 4 I get 8, plus 1/2 of 2 times, again, 8 plus 6, and then plus 1/2 of 2 times 6 plus 0. So those are your trapezoids, which gives you 14, 14, and 6. This is, if you add that up, 34. That's what I was finding. So if you average your left and right side, you end up with the trapezoid rule, not the midpoint rule. So let's change that. This is, yeah, 34. Oh, zoom way in. What are you doing now? So this right here is the average of your left and right, gives you the trapezoid sum. All right. Now, this is really about understanding if you have an overestimate or an underestimate. As we saw before, looking over here, on the left Riemann sum, do you think I'm going to have an overestimate or an underestimate? Being that I'm including all of this area right here extra, again, but I'm not including this area. This area is not included. But still, do I have more area that I'm including versus excluding? In this case, I probably have an overestimate. Okay. Definitely, most likely have an underestimate here. Okay. So let's look at this. If I'm using the right value, let's say I'm going from 1 to 3. 1 to 3. Using the left sum, that's this area right here. Is this going to be an overestimate or an underestimate? All right. So this is a left Riemann sum on an increasing function. That will give you an underestimate. If we do from 1 to 3 with a right Riemann sum, overestimate. So decreasing function, if I use the left, kind of the opposite here. So if I use the left from 1 to 3, overestimate. If I use the right from 1 to 3, underestimate. So you need to understand if I'm using the smaller value or larger value for these Riemann sums. Using the larger value obviously leads you an overestimate. The lesser value will lead you with an underestimate. Trapezoidal estimation. We'll go from 1 to 3 again. If it's concave up, we are adding this bit of area right here. So that is going to be an overestimate. Again, from 1 to 3, we are excluding this area right here. So that is an underestimate. All right. Now, if we are given a chart, charts actually make this really easy. We don't have to calculate anything or really find anything. If I want to use the right Riemann sums, the first thing I need to do is find the width. The width here is the change in each of these. So this is width of 3, width of 3, width of 3, width of 3. Now, the nice thing is if the width is constant, you can make this real easy. If it is not constant, you will have to do each sum separately and then add them up. Okay, the reason why it makes it pretty easy is if you are finding the area of a rectangle with the width of 3, could you just add up all the heights and then multiply all the heights by 3? Yeah. Now, if I'm using the right sum, that means I'm using the number to the right. So I'm using these values here. So on this interval, this would be the right sum. Okay, on this interval, this would be the right sum. On that interval, that would be the right sum. So you just keep going and going. So I just use the right values. I say the values to the right. So 3 times 13 plus 18 plus 23 plus 27. Well, I don't know what that is, so 13 plus 18 plus 23 plus 27 times 3, 243, and this is gallons. So for the right side, 3 times we're using the right values. So here we're using the left. On the left side, we're using the left values. So 7 plus 13 plus 18 plus 23. So 7 plus 13 plus 18 plus 23. And that's not it. 7 plus 13 plus 18 plus 23. Times 3. 183 gallons. Now, question is this an overestimate or an underestimate, and explain why? Now, if I use the values to the right, looking at this, what kind of function is this? Is this increasing or decreasing? Increasing. So using a right Riemann sum, okay, as I have an increasing function, using the right Riemann sum is always going to give me an overestimate on an increasing function. So greater because this is a right. Riemann, I always get that. Oh, dear. I always assume I'm writing that wrong. Riemann sum on an increasing function. Same reasoning for the left. It is decreasing or less. Because this is a left Riemann sum on an increasing function. Now, for the midpoint, now, in this case, it's a little harder because we don't actually have the midpoints, so we would have to actually use the midpoint formula, which is the average between the two. So that means I'm going to be taking, now this is only with two subintervals. So actually that makes this a bit easier. I'm doing this with two subintervals. That means I'm going from 0 to 6 and then from 6 to 12. So my width is 6. My rate of change is 6. And I use the middle values. So 6 times 13 plus 6 times 23, or 6 times 13 plus 23. And that gives you 216 gallons. Now, there is no, like I said, we could, if we wanted to, if we're asked to find the trapezoidal sum, what can I do? Add the left and right and average them together. So that would give you 243 plus 183 divided by 2. So 243 plus 183 divided by 2 gives you 213 gallons. All right. Just to verify this, just to show this works every time. The trapezoid is 1/2 the width, which the width is 3 again, times the sum of the sides. So that would be 7 plus 13. Plus 1/2 of 3 times 13 plus 18. Plus 1/2 of 3 times 18 plus 23. Plus 1/2 of 3 times 23 plus 27. Now, there is a bit of a shortcut here. Notice that everything has 1/2 of 3, which is 1.5. And I include every number twice except the endpoints. So that is 7 plus 2 times 13 plus 2 times 18 plus 2 times 23 plus 27. So I can type that into a calculator a whole lot easier. So 1.5 times 7 plus 26 plus 36 plus 46 plus 27, 213 gallons. And that is it for the notes today.